Good morning, all of you. So, we were discussing the area under the peak or the peak ratio, and then we have discussed this term, that is the integration and the integral value. And so, we are able to find out the integral value for each proton by using the integrations given in the NMR spectrum. But the number of sets of protons which we are getting here in the different molecules, it may vary, and so the number of protons obtained from the integration may be 1 2 3 4. And so here in the, we will just see, that is the, we will see the number of protons obtained obtained from integration and the types of proton. So here, what will be the different types of protons? Means here when we are getting the integration for one proton, if the only one proton is obtained in the integration, that the peak is responsible for only one proton. And so what type of groups may be present? So the group may be CH, means this one proton attached to the CH, or it may be OH, it may be NH, it may be CHO, it may be the COOH, or a penta substituted benzene. So here there may be a substitutions, the different substitutions. So here there is a proton, and these are the different groups attached, and so this may be your this one type of proton, or this one proton will give you a signal. So such type of groups may be possible in the molecule. And so this was the for one set of proton. If you get the number of protons in integration, that is two protons are responsible, then the type of groups may be your CH2, NH2, methylene group, the amino group, then the tetra substituted benzene. Tetra substituted means benzene, means here this one, here the five substitutions are there. Now here, instead of this one substituent, there may be a hydrogen, so the two protons may be present due to such type of tetra substituted benzene molecule. Then the, if the integration value is obtained for the three protons, then the type of group may be your CH3 group, that is the methyl group, or the tri-substituted benzene tri-substituted benzene. So here there may be three substitutions here. So here the three substitutions are occurring, and so here there will be three protons, and these three protons will show you the one signal. Then if the four protons are present, then you will have two CH2 which are equivalent, two CH2 groups which are equivalent groups, two CH2 equivalent groups, or you may have a di-substituted benzene. So the substitution will go on decreasing. Here there are three substitutions, in the another di-substituted means there will be three substitutions, two substitutions only. Then if you get the for five protons, then it is mono substituted benzene, means if you get a signal for the five protons, it will be mono substituted benzene only, means it may be mono substituted benzene. So here the benzene nucleus will have all the five protons, and these five protons will give you one signal, and this is your one substitution, that is the mono substituted. Then the six, if you get a signal for the six protons, it may be three CH2 groups, three CH2 groups which will be equivalent, means the three CH2 groups must be equivalent, must be same in the same electronic environment, then and then only you will get the CH2 groups which are equivalent, will show you a signal of 6 protons, and or it may be two methyl groups, and these two methyl groups will be equivalent, these two methyl groups will be equivalent. So then you may get a signal of 7 protons, and so this may be monosubstituted naphthalene, monosubstituted naphthalene. So the naphthalene structure is there. In this way you may have this structure of naphthalene, and it may be monosubstituted, suppose it is OH. So here you will get the signal of 7 protons. 8 protons you will get 4 CH2 groups, 4 CH2 groups, because there is no any other group that which can give you the signal for 8 protons. So there may be 4 CH2 groups which are equivalent, that is magnetically equivalent, means with the same electron density around that. So 9 protons, it will be 3 CH3 groups, 3 CH3 groups which are equivalent, again magnetically equivalent, means same electronic environment. Then 12 protons, 4 CH3 groups, 4 CH3 groups which are magnetically equivalent. And so in this way, how many protons are responsible for the signal, and so the number of protons obtained from the integration may be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or it may be 12. So depending on this, we are getting these hints. So these are the hints to just study. Then with reference to this, now we are, this was the all regarding the integration and the integral values or the area under the peak, gives you the idea regarding how many number of protons are responsible for that peak, can be calculated very easily or can be seen very easily. And then now the next point that we want to study, that is the splitting of splitting of splitting of PMR signal, PMR signal or peaks, splitting of PMR signal or peak. And this can be, this happens due to spin-spin coupling. This happens due to spin-spin coupling. The splitting in PMR signal or peak arises due to spin-spin coupling. So how it arises, that we want to study. So to understand this concept, that is the splitting of the signal, we will see that a PMR spectrum of ethyl chloride CH3CH2Cl. Now if we take the spectrum of this CH3CH2Cl, means that is the ethyl chloride, we will get a spectrum here, and this spectrum with respect to the 0 del parts per million, that is the TMS signal is here. And so with respect to this, here we are going to get, so these are the two types of protons, that is A and B, and so you are supposed to get two signals. One signal A is responsible for 2 protons and one signal B which is responsible for 3 protons. And so which is shielded and which is de-shielded? So A is de-shielded and B is shielded. And so A gives the signal at 3.4 del. A gives the signal at 3.4 del. And CH2 A proton, this is your B, and the A protons will give you the signal which are shielded than CH2, and so will give the absorption at 1.8 del, 1.8 del. And so here this is due to the A types of protons and this is due to the B types of proton. And so this spectra was studied under low resolution spectrophotometer, So if you want to get the idea that the PMR spectrum of ethyl chloride was first studied under a low resolution spectrophotometer and gave you a spectrum containing two signals, one at 1.8 del and one at 3.4 del. But if this spectrum is taken under a high resolution spectrophotometer, if the spectrum is taken under a high resolution spectrophotometer, so in a high resolution spectrophotometer, what we are going to get? In high resolution spectrophotometer means, what is the resolution? So here this may be your 60, 100 megahertz, 60 megahertz or 200 megahertz, and this may be taken at 300 and 400 megahertz instrument. And when you shift the, or when you change the instrument, and this, you will get the signals. And so here, with respect to the TMS, the first signal A, it was found at 1.8 del only, at 1.8 del only. Here we are getting a signal in splitted into three lines, and at 3.4 del we get a signal having four lines, and so this value was also 3.4 del. And so this is also the spectrum of ethyl chloride, and this is also the spectrum of ethyl chloride, but one spectrum gives two lines, that is one signal at A and one at as B. But here, when high resolution spectrophotometer is there, the chemical shift values are same, that does not change, but the one line has been splitted into three, which is termed as triplet, and one line of B has been splitted into four, and it's called as your quartet. So what happens here? The splitting of the separation of the PMR peaks into number of smaller peaks means this is nothing but your, so the separation of PMR peaks is known as splitting of PMR signals, or the PMR is known as splitting. And so when this splitting is taking place, why this splitting is taking place? Because we say that this magnetic nuclei and these two magnetic nuclei are having the same electronic environment, and these three magnetic nuclei are having the same magnetic electronic environment. Now the electronic environments are different, but these nuclei are also spinning around their own axis and creates a magnetic field. But this spinning of these two nuclei is having a different type of precision, and these three protons precise in a different way because the electronic density is different. And so the spinning of these three protons affects the spinning of these two protons, the neighboring protons. These three protons, when they are spinning around their own axis and creating the magnetic field, this interacts with the neighboring protons, these neighboring two protons which are magnetically equivalent. These are magnetically different. CH3 and CH2 protons are magnetically different, but CH3 protons are magnetically same, and CH2 protons are magnetically same. The spinning of these three protons interacts with the spinning of these two protons. As these three protons interacts with these two, in the same way these two interacts with these three, and that's why there is a spin-spin coupling. Spin-spin coupling. And so due to this spin-spin coupling, when the spinnings of these different kinds of protons are interacting with each other, it splits the signals into the different patterns. It may be one signal can be split up into two, or one will remain one as it is, one will split into two, one may split into 3, 4, 5, 6, any type. And so this splitting pattern depends upon the number of neighboring protons. And so how this spinning couples, this splitting occurs due to the coupling of the spin states of the given nucleus with the spin states of the adjacent or the neighboring nuclei. That is the spin coupling, and this is caused by the splitting is caused by the coupling, spin coupling of the different nuclei. And so we will just elaborate this in the next lecture, and we will thoroughly see that how this interaction or this spin coupling is taking place and how this splitting is taking place. So thank you very much. We will continue in the next lecture tomorrow.